Let us now understand the concept of gate delays and critical path. Consider a half adder circuit with two inputs A and B and two outputs, the sum output which is A XOR B and the carry output which is A and B. The circuit has two gates in total, the XOR gate and the AND gate. Every gate in a circuit has a gate delay, which means that if you give an input signal to the input of the gate, it's going to take some time for it to produce an output, and that is known as gate delay. Gate delay is typically represented as GD, and it is in the order of few nanoseconds. An XOR gate can have a different gate delay compared to an AND gate or an OR gate or a NOT gate, and a NOT gate can have a completely different gate delay from a AND gate, OR gate, or an XOR gate. The critical path of a circuit is nothing but the path which has the largest amount of delay. For the half adder circuit here, assuming that both the gates have a same delay called GD, let's assume that both are equal. The critical path of the circuit is one gate delay. Okay, now let's consider a full adder. So the sum equation is A XOR B XOR Cin. The carry out would be A and B or Cin and A XOR B. The other forms of the carry out are A and B or Cin and A or B. This is another form. They both are functionally correct. And the third one is basically I take the second one and I multiply out everything. Okay, this is equation 1, 2, and 3. 2 and 3 are clearly equal. 1 is also equal, but it's going to take some more math to find out why 1 and 2 are one and the same. But assume that we have three equations here. Now let me construct the circuit for the three equations. So for the first circuit, we have already seen this. You have A, B, and Cin. A and B go into an AND gate, and then you have A and B go into an XOR gate. Then you have Cin, which is ANDed with the XOR output, and this one is ORed. So that's C out. As you can see, in this case, assuming that all gates have a gate delay of GD, the critical path of the circuit would be, so if you take the upper path, it's going to be this gate delay and this gate delay, but that's only two gate delays. If you take the lower path, it's going to be GD, one gate delay. This feeds into another AND gate, so the AND gate is waiting for the XOR output, and the AND gate undergoes another delay, GD. And then you have the OR gate, which has another GD, so that's three gate delays. Therefore, the critical path for a full adder with equation number 1 has three gate delays. So critical path has three gate delays. Let's take the second equation, which is AB or Cin and A or B. So we have AB, they are ANDed together, and then you have Cin, or let's do the OR operation between A and B, and finally you have the Cin, which is ANDed with this result, and this is ORed. Again, assuming that all gates have a gate delay of GD and they are equal, the critical path again will have one gate delay, two gate delays, and three gate delays. We cannot take the upper path because that's only two gate delays. So C out, you're guaranteed to get after three gate delays. Therefore, critical path for the second equation would also be three gate delays. Let's take the third equation, which is AB or BC or AC. That's A, B, C. So you have AB, you have BC, and you have AC. All of these three go into an OR gate and you get C out. Here, assuming again all gates have the same gate delays, in this circuit you can either take this path or this path or this path, but you would undergo only one gate delay because all of them are happening in parallel. The operations are happening in parallel, so that's one gate delay. And then you have an OR gate which has another gate delay, so that's two gate delays. Therefore, the critical path has two gate delays. Out of these three circuits or these three equations, the third equation incurs the least amount of gate delays, or it has the least critical path. Therefore, circuit number 3 is going to be the fastest. Now you might be wondering why I took only C out and not S. If you remember, the S equation is A XOR B XOR C. So it can be represented as ABC. Assuming you can only have two input XOR gates, the critical path would be two gate delays. But C out has at least two or three gate delays. That is why I wanted to show you the difference. So the full adder has two gate delays, and the half adder has one gate delay. Even though circuit number 3 had the lowest amount of gate delay compared to the other two circuits, circuit 1 is typically used because it is easy to implement. We study critical path for two main reasons. The first reason is timing analysis. The second thing is, which is perhaps the most important thing, is the critical path decides your clock frequency. If you remember, when you open up your Windows and you go into DXDiag, or if you want to see your system properties like your processor and the RAM speed, etc., you would see that it might say something like Intel Core i9 working at 2.4 gigahertz. So this frequency is decided by the critical path. So if your critical path is high, then your frequency of operation will be low. Therefore, your processor speed will be low. And if your critical path is low, you can increase your clock speed and you can have a better performance.